So now let's look at a few example problems from Module 6.2. So let's take a look at this explosion problem here. So we can see we have this larger mass M over here before the explosion. After the explosion, it breaks into smaller masses A, B, and C. So now they tell us that the original mass M is 100 kilograms and has an initial velocity v sub I of 20, acting purely in the j hat direction. Now they tell us that mass A over here after the explosion is 20 kilograms and has a vector, velocity vector of 50 I hat plus 50 j hat meters per second. Mass B has a mass of 30 kilograms and a velocity vector of negative 30 I hat minus 50 k hat in meters per second. So of these three smaller pieces here, how they want us to find now the velocity of the fragment C after the explosion. So that's the only one that they don't give us here, is we need to figure out the velocity of this fraction of the mass here, C. So our plan, since the internal forces of the explosion cancel out, so that's going to be very helpful through our solution, we can apply our conservation of linear momentum to the system. So we're applying this to the system right here. So now that we've read through the problem statement, our next step is to create the setup page here. I redraw out my diagram showing the larger mass M before the explosion with its velocity v sub I, and then we have VA, VB, and VC of the individual particles after the explosion. We have our mass of our big M before the explosion, our mass of A, and our mass of B after the explosion. We have our initial velocity vector for the mass M. We have our velocity vector for particle A and velocity vector for particle B over here. Now what we want to do is use our conservation of linear momentum to find C. So what we have here is M sub C for our mass is equal to our large whole mass M before the explosion minus MA minus MB. So from that there, we can plug in our known values where our large mass M here before the explosion is 100 kilograms, our mass A 20 kilograms, mass B 30 kilograms. So from that there, we can just get our mass of C. So we need our velocity vector for C next. So the next thing we want to do is the velocity of fragment C after the explosion. We'll call this our V sub C. So now for our solution here, we can use our governing equation here, big M, our mass before the explosion, our total mass here, times V sub I, given to us in the problem statement, is equal to MAVA plus MBVB plus MCVC. Now we solve for all of our masses. We have MA, MB, and MC. We were given our VA and we were given our VB. What we don't know is our VC. Now there's three components to our VC. It could be acting in X, Y, and Z direction. So we have one equation and three unknowns down here. So we have our VCX in our I hat direction, our VCY in our J hat direction, and our VCZ in our K direction here. So what I want to do is break this down into three equations, because technically there's three unknowns. Our three equations will correspond to our X, Y, and Z components, or I hat, J hat, and K hat unit vectors here. So we want to equate the components on the left side. So let's just look at our I hat, or our X component first here. Go through the entire thing. Well, on the left-hand side of our equation, there is nothing acting in our I hat direction, only our J hat there. So 0 is equal to, now this first part here, we can say this is 1,000, because we have 20 times our I hat. I'm color-coded in yellow here, so you can see how I'm dealing with each of my components separately. Minus our second term up here is 30 times 30, or 900. And our last one here, it's 50 times our V sub Cx. So therefore, we can solve that our only unknown here is this V sub Cx, so our V sub Cx is equal to negative 2 meters per second. So now we've just found our X component of our velocity of C. So we do the same thing for our J hat, and on our J hat here, it's 100 times 20 on the left-hand side, so that's 2,000 right there. Now we have 20 times 50 is 1,000 from our second part of the equation here on the right-hand side. And now over here we go to a 50 Nothing acting right here in this one here. All we have is the last component is our 50 times our VCY. So 50 times VCY, we can solve this out. Our only unknown is the VCY, which is 20 meters per second. So then we can go lastly to our K hat or our Z component here. There is no Z component on the left-hand side of the equation, so that's 0. This is equal to, there's no Z component in the first term on the right-hand side, so this is equal to negative 1500 from our 30 times our 50 over here in our K hat direction, plus our last term over here is 50 times our VCZ. Solve that out, our VCZ is equal to 30 meters per second. So we can now create our vector here and say that V sub C is equal to negative 2 in our I hat direction, plus 20 in the J hat, plus 30 in the K hat in meters per second. And this is for immediately after the explosion. So next, let's take a look at this train problem here. So in this problem here, we're given that two rail cars have masses of MA is equal to 15 megagrams and MB is equal to 12 megagrams. So here's your MA here, here's your MB there. And the velocities are shown here that the velocity of A is moving to the right at 1.5 meters per second, and the velocity of B is moving to the left at 0.75 meters per second. They want us to find the speed of the cars after they meet and connect. Also, they want us to find the average impulsive force between the cars if the coupling takes place in 0.8 seconds. So what's going to be important here is we're going to need to choose a coordinate system. We could go with the standard Cartesian XY, where we have x positive to the right and x negative to the left, or we could do the reverse of that, and that'll just mess with the sign convention between car A and car B. So our plan for solving this problem is first to use the conservation of linear momentum to find the velocity of the two cars after connection. All internal impulses will cancel, and then use the principle of impulse and momentum to find the impulsive force by looking at only one car. So now that we've read through that problem statement, the next thing we want to do is create our setup page here. So for this example here, I simplified down the diagram here. So I have my car A moving to the right at 1.5 meters per second. My car B moving to the left is 0.75 meters per second. I chose to go with the standard XY Cartesian coordinate system where X is positive going to the right and Y is positive up. So that means that car A will have a positive velocity and car B will have a negative velocity. So I come down here and I say, okay, my mass of A is given to me as 15 megagrams. I want to convert that to kilograms right away for my problem solving. So that's 15,000 kilograms. My mass B is 12 megagrams or 12,000 kilograms. My velocity at A is 1.5 meters per second and my velocity B is 0.75 meters per second. And now according to this coordinate system, this would be a negative 0.75 meters per second. So with that information from my setup page, I can now begin my solution here. So my solution, first thing I want to do is use my key equation for the conservation of linear momentum. Deal with this in just our x direction here. So what we have now from our conservation of energy equation, we have the MA VA1 plus MB VB1 is equal to the mass 2 is the mass they combine because they join together after the collision here. So the mass here, or capital M, is MA plus MB times this now velocity they're moving together, velocity 2. So it simplifies down this conservation of linear momentum equation by MA and MB becoming capital M, and our velocities moving together. So I can plug in my known values here. My MA is given to me now that I've already converted to kilograms is 15,000 kilograms, 1.5 meters per second. Mass B is 12,000 kilograms, negative 0.75 meters per second. This is equal to, we can add those two masses together, 15,000 plus 12,000 is 27,000 kilograms times our V2. V2 is the only unknown in this equation from our conservation of linear momentum. So our V2, when we solve it out, becomes 0.5 meters per second. So a couple key things we really need to do. We need to convert to kilograms, and we need to pay attention to our sign convention here for our velocities, and also realize that after the collision, these two join together. So as we move forward here, what we want to do is use the principle of linear impulse and momentum. Do that for one car. So let's do it for car A right here, and we're only going to look at our x direction here. So we have MA VA1 plus our integral of f dt, which is what we're looking for here, equal to MA V2. We can start plugging our knowns. We know that MA is given to us as 15,000 kilograms. Our VA1 was 1.5 meters per second. Our integral of f dt is what we're searching for here. Our MA is given to us as 15,000 kilograms. Again, and our V2 we just solved for is 0.5, our only unknown here. We can solve for this as our integral of f dt. So our integral of f dt is equal to our negative 15,000 Newton seconds. So we go through this here, and we can actually do out this integral if we need to. So the integral of f dt, evaluated from 0 to 0.8 for our time there, of 15,000. We do that out here, so we do out our integral here. Integral of f dt becomes f is constant, pull that out front there, a dt becomes t. So we have now fa average from our integral of f dt times our time is equal to 15,000. So we can plug in our value here for t from our limits of integration. So f average times 0.8 is equal to 15,000 Newton seconds. So we rearrange, solve for f average. F average is negative 18,1750 newtons. And again, which coordinate system we use depends on what's positive and what's negative. So now we chose to do this with car A. We can go through and do the same thing with car B. It's the same general equation, but now it's mb VB1 plus our integral of f dt is equal to mb vt. V2 over here, plug in our values here, and now we're dealing with 12,000 and negative 0.75 for our velocity there is equal to the integral of f dt is equal to our 12,000 times our V2 over there. We can plug in our values here, end up with, we still have the same relationship over here, 15,000 is equal to the integral of f dt. It's just that this is for car B now rather than car A. It doesn't matter which one you chose. Sign convention will be slightly different. But when you get down to the end, you're going to find that you find the same f average regardless if you went with car A or with car B. And the integral is the same over here. When we do this for car B, we have our integral from 0 to 0.8 of f dt is equal to now our 15,000 over here from this as well. And we pull our f average up front is equal to the integral from 0 to 8 dt is equal to 15,000. So f average, take the integral of dt becomes t, evaluated from 0 to 0.8 is equal to 15,000. So f average of 0.8 minus 0 is equal to 15,000. So we got that same relationship that we saw here and here. So it's going to be the same f average when we do it, regardless if we use car A or car B.